So it's pleasure to speak here and show our achievements in this direction. So basically, this is a specialization technique which has some particular distinction from other specialization approaches, and also some evaluation technique or stages of evaluation. I will go to describe first, in a nutshell, what is isomorphic specialization, then why it is matter, and also why it is matter to have first-class isomorphism in the system, and also how it works. So program specialization is like a 40 years history study of partial evaluation, where you have some program with two arguments, for example, and if one argument is some known value, like constant, then you can automatically transform this program into another program, which is equivalent to the original program. And it's better sometimes. Another specialization techniques, which is also well known in the supercompilation, where you have P is a program which X should be belong to B, and you specialize this program into some P prime, where X is in some subset of B, and also some equality property holds. And isomorphic specialization in this line is formulated like this. If you have a program from A to B, and you have some isomorphism from A to A prime and B to B prime, then you can automatically transform this program into P prime, such that the diagrams can be. I will explain how it works on the next slide. So let's take as an example matrix vector multiplication problem. And this problem can be expressed as a program in some functional language. It's called by Scala. So what we can do here, we can use abstract data types, like matrix and vector, whatever matrix and vector it is. And this program produces also vector. And we can take some rows from the matrix. Also, we can map an array of rows into another array, and we can construct a new vector from this array of values. So, what kind of language we use in here? So it looks like Scala, but in fact it is embedded domain-specific language, which is defined like this. We can erase interface with two methods. We can use it like this. And we have vectors, which we can use methods like this. And also we have a matrix. And for this particular example, we need only this method, just to minimize this language. But this language can grow as a domain-specific library, for example, in Scala. So this means that embedded domain-specific language. So this is what is necessary to write this particular file. And the outline of the specialization method is like this. If you have some number of domain-specific languages and you implement this abstract implementation of some algorithm, then you can apply isomorphic specialization transformation, which allows you to produce concrete implementation of this algorithm using some core language, which will be defined in the next slide. And then, if you have an efficient compiler for this core language in this work, I will show how we use LMS compilation framework for domain-specific languages and how it works in this context. So, core language is like this. So you can select, in fact, any language you want. It's just a matter of choice which core language you want to specialize to. So, but you need to have data types in the language, and we use some family of data types. And also, we use one constructor array, with some methods, which is abstract interface. And also we have some primitives, which is also the part of this core language. It means that if the program is written and formulated using these methods, it can be efficiently compiled and do something. So now if we have a compiler from core language into something executable, then we can implement abstract data types using this core language. So let's look at implementation. So we can use array language, for example, to implement dense vector. In order to implement dense vector, we can extend this vector interface, and we need just to implement some methods that are declared here. And notice that here is primitives of the core language, and this is the type of the core language. So it means that this is a complete implementation of this abstract data types using subclassing in object-oriented style. So it implements interface used for language primitives and types. So by default, we can assume that if we have an array of values, then we can construct a dense vector from these values. And this is also our choice as a programmers. And then in this abstract implementation, we don't know how matrix and vectors are implemented. And this is a key point. This method is completely abstract in terms of how these objects are implemented. So in order to execute this particular code, what we usually do, we have some core data, which is, this is the types of the core language. Then we wrap this data into some objects, and then we just apply this method MDM, and then we get the values of the resulting vectors back. This is like three-step process: wrap, apply, and extract. So the outline of this method, like version 2, is like this. If we have an abstract data type and some set of concrete implementations of this abstract data type. For example, if it is vector, then we have many different implementations of vector. And also we can have matrix, and also many different implementations of matrix. These implementations implemented using core language, which is our choice. Then we can use this system of embedded DSLs as a library to develop abstract algorithm, for example, for this particular task, and get abstract implementation. So this code is abstract implementation of this task. Then we can take isomorphisms from concrete implementation. I will show how we get isomorphism from this description. And as a second input to isomorphic specialization algorithm, it allows to produce specialized code for this abstract implementation. And the key point is that this code is implemented in a core language, so this particular version, it doesn't contain any domain-specific object. It's a core language, and all these abstractions are removed from this process. Why it is important? Because we can use the same core language to keep the core data is some data that you have. Usually in some media you don't have objects in some media, you have some serialization of the data in arrays or some other data format. So this can be a core language. Then you can compile specialized code into something executable and execute this function producing from core when data to core data. So this is how and because this is a staging approach, this isomorphic specialization can happen at runtime. It means that runtime data can participate in selection both isomorphism and which particular implementation to use as part of this method. So again, if we have the task to use matrix and vector abstract data types, then we develop some abstract implementation. Then we apply staged evaluation of this method, where it's a point where staging comes into the scene. We just in staged mode evaluate this function and apply graph rewriting rules to produce this code. So the staging part is like a transformation media when we come from this formulation of the problem to specialized version. So how this works? If we have, for example, definitions like two vectors which are dense, and these two vectors wrap v1, v2 is an array. This is the definition of dense vector. Then we can apply staged evaluation for this particular term. And what's going on here is that here we have the rules according to semantics of object-oriented language. When we have an object with these parameters where every field is also a constructor. It's in a sense of away Java formalization of object-oriented language. If we take one field from this object, then we just get v1. It's a reduction step. And then we come to this, and then the same applies to second radix. We have this, and this term already don't have radixes, so this is the final. And another example, if we have this big term here, because during staging we can apply rewriting, there is a rule which says that we can fuse two maps together. And in this particular case, f is defined like this. So this is one thing, this is another thing. Then it goes to this composition. Then we apply records according to evaluation of the language semantics. And we get this. And again, we apply rewrite rules. Then we get the final result. So this combination of applying language semantic transformations and rewrite rules as a transformation of the process allows to keeping the semantics of original term to go to specialize it into some like normalized form. So the key point so far, develop an algorithm using abstract data types of embedded cells, implement abstract types using some functional core languages in efficient compiler, and specialize in abstract code into the core language. And so why it's matter? It's because from this abstract definition, through isomorphic specialization, we come to array computation, and by applying aggressive optimization of this core language, which is focused on array transformations, we can get purely imperative code which is optimal for this particular data types that we selected here. So this is just dense representation of the matrix. This is dense vector, and this is imperative code for the task of multiplication. And so if we try to run on this experimental data where we have a matrix of some reasonable size, and we have different sparseness of this matrix, and if we run original version as object-oriented program, we get these digits. But if we apply first isomorphic specialization, which transform and specialize with respect to data representation of dense matrices into the core language and then use optimized compiler, with this we have this performance improvement, and everything happens automatically. So first class isomorphism is important point here, because we know that we can, for example, if we take a matrix, we can represent this matrix in some dense format. This is an array of pointers to some array of values. All arrays are of the same size, and this is just a row of the matrix. But we can also represent this matrix in a completely different way, where we have sparse representation of rows. This is a column index. This is a value that we want to keep. This is a pair. It's like an array of pairs, and we keep each row in a single pointer. So this is different representation. But we can also represent this matrix in so-called flat sparse matrix, where we keep all the rows in single flat arrays, and then we describe the length of each row. So the claim is that this representation is isomorphic in some sense, because we keep all the necessary information. For example, this 4 is necessary because based on this representation, we don't know how many columns in the matrix. We need to know this. In this case, we can produce automatic transformation between these alternative representations. And in this sense, all these representations are isomorphic. So the first class isomorphism is when you use this factor that we have a lot of different isomorphic representations for data structure in order to make them user-definable. It means that, for example, if we want to develop a vectors DSL, for each DSL is just some interface and operations around this abstract data type. So the vector is just an abstract type, and we can develop 2 different representations of the vector, and have some conventions that, for example, if we get all the arguments of the constructor, then we can automatically get the core language type from this argument, which is our representation of this object. So it's just by convention and user-defined. And this is another user-defined code where this is a number of core data types which represent our data. So the isomorphism with this type. And the same happens with matrices. It's also our choice of interface, our choice of representation, and implementation of these methods is inside this class. So far, this is just a usual object-oriented approach to designing some domain area and the domain data types. But because in this system, this particular choice of data representation is first class is library. The system takes all these interfaces infer from these descriptions. So
question?
Yeah.
So you said first class isomorphism, but I only saw sort of data type definitions. Where are the isomorphisms, the functions between them?
Yeah.
Are they user defined or
this slide.
inferred?
Yeah, this slide. Yeah.
So the isomorphisms weren't there, they're coming.
Yeah, coming. I will explain this time. So the generic idea is that once we have these functions from domain types here, to some core type, this already it's like identity function but between fields and this type. But it is isomorphism between this type and this type. So why it is, so how isomorphism are constructed and why is they first class value is because if we have a family of types in a core language, then for each constructor of the core language, we can produce a composition of isomorphic in a generic way. So we have iso product, which is isomorphism between products, and iso plus, which is isomorphism between coproduct, and also for array, which is isomorphism between arrays. And how it actually works is that every time you have a value of type sigma, which is domain type, or like a matrix or sparse matrix, and if you have some value 10 of type T, which is a core type, then you can represent this value as a composition of this type with an isomorphism from T to sigma. So in the intermediate representation, we have this view which allow us to describe this composition. And why this isomorphism is important is because if we have this abstract formulation of our original task, then applying different isomorphism, we can automatically generate two alternative specializations. So this is different, and notice that here we have dense representation, and here we have different representation, different type, and this is a sparse representation. And as a consequence, we have different code here, and these versions are generated automatically. So why these different representations also matter is because we not only by transforming to core language and then optimizing and getting this speed up, if we have this automatic generation of different specializations, we can just generate everything, and then for each particular data sparseness, we have the winners, which one is the best for this particular data structure. And it is not always the same, so it changes. And the key point is here. It's not obvious in advance that this particular implementation is the best choice. Because, for example, the intuition may suggest that because it is 50-50, maybe sparse representation will be better. But in fact, full sparse representation is like five times slower. So it means that if you care about performance of this abstract code, you should have this selection for free. And the remarkable property of this isomorphic specialization algorithm is that if we have this setup where we have program from A to B, some isomorphism, and we transform from P to P prime, then if A and B is the domain types and A prime, B prime, core language types, then this isomorphism, the two part of the isomorphism, is a wrapper which wraps this core types into some domain abstraction. Then we have this transformation from abstract type to abstract type. And then we have an extractor which takes from here to here. And the conjecture, which is proved by practical applications, is that it holds for all these combinations. So for all programs, and isomorphism always exists this P prime, which is the result of applying stage evaluation with specialized rewriting rule to this particular composition. And this P prime is a core program written in a core language. And the final slide is how it works. So it works with a graph, and the key point is here. When we have in the graph some method call, and the method, this call is just in the following the semantic of virtual method call with this language. And the idea is that we implement semantic of virtual method calls and stage in time using intermediate nodes as instances. So literally we take an instance of the graph and call the method of this instance. And what happens is the result of this application, which is according to semantic of the object-oriented language. So this method call just inline into this particular graph and rewiring happens. And this is a regex, and this is not a regex because this is variable, and we cannot call this method. But we can call this method and get R because we know this is an instance. So this is the general scenario. So we develop an algorithm using abstract data types. We identify isomorphic representations in the domain. This is user responsibility. We implement abstract type using core language, and we generate representation-specific implementation with the core language. Then we use optimize the compiler, and you can check it out and try for your domains. Thank you.
So there is this famous quote that all problems in computer science can be solved by adding a level of indirection, right? And that means going into something more generic than the problem. But this quote actually has a second part, which says that this is only true for problems except those caused by too many levels of indirection. Right? And those problems are usually performance problems, right? If we add more indirection and more generality, then things become slow. So just to give a bit of context, so I think this is a really, really important piece of work in the sense that it actually shows that we can take the well-known techniques from generic programming, like first-class isomorphisms, to actually solve the problems caused by too many levels of indirection as well, by including the specialization and code generations. In terms of questions, so your paper has, there are several things, right? So you have experimental results, you also have formalization, and you also have like code examples. So I would be interested to know about sort of how did these pieces come together? Did you first work on the formalization to figure out how to do things and then implement it, or was it the other way around? Or how did the implementation and the formalization interact?
So the original idea was that let's take this idea as a first step. What if we can call the methods of the nodes of intermediate representation? And because we have this like dynamic method call using virtualization, when we do it in staging time, we really like virtualizing building of the graphs. So this was an idea. So in some sense, until we call these methods, we don't know which graph it will be. And it depends on the concrete tab here. If we just replace this node, single node of the graph, we replace with different object, the same graph with the same semantics will give completely different graph here. And this was the original idea. And it was implemented 2 years ago.
Okay, so in the interest of time, maybe one or two quick questions from the audience. Any questions?
So I've seen you talked about large performance increases, but have you compared the original, the different implementations that you have against specialized linear algebra packages to know, are you performing as good as, say, if you would take something in C or C++?
Yeah, we didn't work in this particular context. Is what is important is to get the code that you usually write directly in imperative stack. So if you, for example, using Scala, and you would write this efficient solution for this particular problem using selected representation of data, you would write this particular final code. So in this particular case, we show that this code can be the result of the automatic procedure and transformation from very short high-level description. That's all. We didn't compare with, for example, C++, because C++ can be more efficient than Scala.
I'm just curious, you know about Spiral, right? How do you compare with Spiral?
I'm not.
Oh,